do have questions after my presentation, we have a little booth out there, and please do come and see me, and I'll share more information with you. So I'm going to talk about a technology today that is not up in the clouds like the drones that we've seen recently, which was quite interesting. It's also not LiDAR, but it is a technology that is faster, safer, more detailed, and actually just as accurate as traditional survey. Very briefly, an introduction, I work for Pavemetrics. Pavemetrics is a Canadian company, and we're a spin-off of Canada's National Optics Institute, or INO. And our sole focus is the development of 3D scanning systems and algorithms for inspecting infrastructure. And they're used around the world to scan everything from roads to runways to railways and tunnels. And we're in more than 40 different countries, and we've sold more than 400 systems. This is a technology that I'm going to talk about for the next few minutes. It operates on the principle of laser triangulation. I'm not going to go through all of these bullets, but I do want to point out a few of them that I think are really key. This is a technology that can be used day or night. It has its own illumination system. It can be used at speeds up to 100 kilometers per hour in a road environment. In a rail environment, this same technology can be used at speeds up to about 160 kilometers an hour. Has a 1 millimeter resolution in the X and Y, and it has 0.5 millimeter resolution in the Z. And in fact, the latest version of this sensor has 0.1 millimeter in the Z. And it offers a 45 megahertz scanning rate, and importantly, we bundle it with automated data processing algorithms. So here's a typical installation for a road type environment, and you can see it's mounted on the roof of the vehicle. The red circles show us where the sensors are. We also have inertial measurement units on board, GPS, and a DMI, which measures linear distance. In the rear of the vehicle, there is a power supply and a computer for storing the data. And then typically, the system is operated from the front of the vehicle, either a laptop or simply a screen connected to the computer at the rear. So as I mentioned, this is not LiDAR. So let me compare and contrast this to LiDAR for you, because I'm sure most of this audience is pretty familiar with LiDAR. So LiDAR is a time-of-flight technology. We take a pulse of light out, we send it to an object, and we measure how long it takes to go to the object and come back. And because we know what the speed of light is, we can then translate those times into distances. LiDAR is a great technology if you want to scan something large. As we saw in the drone presentations, you can take a LiDAR sensor up in the air and you can scan a whole field or a whole subdivision. It's not huge resolution, to be honest. It's about 400,000, 500,000 points per second, maybe all the way up to 1 million. The relative accuracy, if you're doing everything really well and you're in a terrestrial situation, is about plus or minus 5 millimeters. And as I said before, you can be up in the sky, so you can be a few kilometers away from the object that you're scanning. This sensor, on the other hand, the Laser Digital Train Modeling System, works on the principle of triangulation. So there's a triangle that's formed between the rectangular window on the bottom of the sensor, the circular window on the top, and where those two windows are pointing on the surface that's being scanned. This sensor is much better focused or utilized for smaller surfaces at higher resolution. It's about 100 times the resolution of LiDAR. Okay, so 400,000 points per second versus 45 million points per second. And from an accuracy standpoint, instead of plus or minus 5 millimeter, it's plus or minus 0.5 millimeter. Okay? However, it's really only useful over a couple of meters. So you can't put this on a drone into the sky. It's not going to work. So big picture kind of perspective, LiDAR is like a landscape lens. Okay? You want to see the big picture. You want to see what's going on. We're more like a macro lens. You want to see all of the finer details, then our technology is well suited to that. This is an example from our sensor. It's showing pavement. This is a combination of the intensity image that the sensor captures overlaid on top of the 3D wireframe model. And the last piece that's on here is the results from an automated algorithm that we have developed that automatically detects all of the cracks down to 2 millimeters wide. And the different colors here correspond to the different widths of cracks. So I'm going to jump into a case study. This is a recent project that we performed in Detroit to compare this technology to traditional survey. It was on the I-75, 1.3 kilometer long section, 3 lanes of concrete. Ground truth was traditional survey. We collected the same site using 3 passes of a vehicle equipped with the sensor at 100 kilometers an hour. We also had an inertial navigation system on board, and we had a local base station set up. Okay, so workflow for the project. First stage, create a ground truth. Survey points captured every 100 kilometers, or every 100 meters rather. Then drive that same network using the LDTM with the inertial navigation system on board and a base station. Then do some office processing. So first prepare a dynamic solution. So this is the vehicle path. The next thing is to take that dynamic solution and to correct it with some of the control data. And then lastly, to stitch those 3 passes together to complete create one complete surface. And then the final stage was exporting to LAS and other formats. So here's the site in question. You can see there are 3 lanes. Here's our ground control points every 100 meters. We did 1 pass in one direction, turned around at the end, came back and did another pass. Turned around again, did a 3rd pass. And you can see between these passes there's a little bit of overlap there, and that's important because we want to stitch everything together in the end. So the ground control, as I mentioned, was every 100 meters. Survey was performed. It was at the edge of the 2 outside lanes, and that data was converted into UTM. And you can see the control points are actually on the top of concrete joints. So these are things that are not going to move, and they're easily identifiable in the images from our system. There was a base station on site while we did the mobile data collection. As I mentioned, it was 3 passes at 100 kilometers per hour. If you look at this top image, this is what you would get if you didn't have inertial measurement units on board. So you can see there's all kinds of impacts to the images that were captured due to vehicle motion. The next image down is a corrected scan of that same road having that inertial data. And then the last piece of the puzzle is a vehicle track using the blended inertial navigation system, which is on the bottom there. So in our industry, Planix is very much a well-known brand name. They produce some of the best inertial navigation systems. We used a PAWS LV420 on board. We use a PAWS Pack software to prepare the dynamic solution, which takes a vehicle path, pitch roll and heading from the IMUs, and base station data. Then we bring that solution into our software. This is our software we're looking at here now. And it's really hard to tell in the image here, but in the center of this circle is the ground control survey point that we've brought in. And just slightly above and to the left of it where the pointer is now, there's a green dot, and that's a dynamic solution. That's the result of using the Planix solution. So very, very good. However, we want to make it survey grade. So we brought in 2 of the control points. Even though there were lots of them, we brought in just 1 at the beginning, 1 at the end of the 1.3 kilometers. And we use that to correct the complete data set, shift everything down and to the right effectively. So the next problem is we've got 3 passes, and there's no way you can possibly start those passes at the same point and end them at the same point. And that means that things don't quite line up. They don't look very good. So in this example here, again, it's a little bit hard to see, but in the middle of the circle, you can see a joint in the concrete, and we put the 2 passes together without doing any correction, and it doesn't quite line up. So we have an automated stitching process. So here's a feature that's visible in 2 passes, and that's why at the beginning I mentioned we had that overlap zone, because I want to see something in both of those scans to bring things together. So here's a little feature on the surface. It's a rock on the surface of scan 1 and scan 2. And here's our software overlapping those 2 scans together and automatically stitching them so that I've got one complete surface after that stitching. And then, okay, my joint looks the way it should. There's no notch in the middle anymore. So then at the end of the project, we created various outputs. LAS was one of the outputs that was required by the client. I'm going to tell you why LAS is not a good format, although most of you probably know. But we'll talk about the amount of data in a second. It took about an hour to do the processing. 15 minutes in PAWS Pack, which is correcting for that dynamic solution. About 5 minutes to align with the 2 control points. In this case, the stitching took about 30 minutes. That was before we automated that in our software. Now it's about a 5 to 10 minute kind of effort. And then outputting to the LAS is 3 to 5 minutes of computer time. So it took about an hour. If we were to redo this, it's probably closer to 40 minutes now. Okay, so why did I say LAS wasn't a good choice? Well, we generated 3.2 billion points across 3 lanes on a 1.3 kilometer section. That's a lot of data, way more than you can handle in LAS. It's really not a great format for that. From an accuracy standpoint, those 3.2 billion points were to an accuracy of 9 millimeter in the X, 10 millimeter in the Y, and 6 millimeter in the Z. And this is not relative accuracy, this is absolute real-world accuracy. Just 2 control points, one at the beginning, one at the end. And as I mentioned, it was about an hour of data processing. So nice little case study on using this sensor basically to not entirely replace traditional survey, but really dramatically reduce how much traditional survey you have to do, still get the same accuracy, much safer for staff, much more data, etc. And just before I leave you, a couple other applications of this same sensor. So we're an algorithm company. We develop automated algorithms to process the data from our sensor. This sensor can be used to provide a complete pavement inspection, cracking, rutting, roughness, potholes. Same sensor can be used in a rail environment to automatically look for rail safety issues, whether it's fasteners that are missing, it's ties that are cracked, it's gauge or spacing of the rail that's out of alignment, or switches that are worn out. And the same sensor can also be used in a tunnel environment, again, looking for things like cracks, poor panel fitment, moisture, those types of conditions. And with that, I'll wrap it up, and thank you. I think we're mostly on time.
Now, I would request Mr. Stephen Way, Product Manager, High Target, to share his thoughts.